red eye comes about in the following way. Here's the eye. It has the cornea. It does a lot of the focusing. And then it has the lens, which at least for young people has a muscle around it that can contract and squeeze the lens to make it more curved so that light will focus, ideally, it will focus on the retina. Like that. If the object is close, you have to bend the light more because the light, instead of coming this way, is coming this way. So it has to be bent even more. So you make the lens fatter to bend it even more. If something's far away, it comes in just like this. Some people's cornea is curved too much. And so it works fine for close things. We say they're nearsighted. But there are people who like to read all the time, and they're craftsmen, and that's great being nearsighted. And then there are people who are hunters or baseball players. And they have to be able to see a distant object coming at them, or a tiger in the woods that's about to, not golf, this is a lion in the woods that is about to attack. You need good distance vision. Now, in my case, I like distance vision because I like to go outdoors. I'm happy to put on glasses like this. I've lost my accommodation. But my vision for outdoors this wasn't really set for outdoors. My lens was too strong. I was nearsighted. So I had what's called LASIK vision, LASIK surgery, which is an optional surgery you can do, a little bit dangerous. What they do is, sorry. Those of you who are queasy can close your ears right now. You don't have to listen to this. This is not going to be required. Okay? Warned? Okay. What they do is, here's the eye. You lie down. And there I am lying down. And they put a little local anesthetic on this, but it's really a quite comfortable and very interesting procedure. Then they take a nice little knife. It's a little vibrating knife. Bzzz. They don't tell you it's a vibrating knife, but I know it's a vibrating knife because I can hear it and I know what's going on. They don't like to tell you that the knife is now cutting your eye, but that's what it's doing. It makes a neat little slice like this. You're lying there on your back, you're just looking up. And then what they do is they take this slice. This is the queasy part. So you can cover your ears. And they fold it back. There's your sliced eye. Now they take a laser. Do I have my laser with me today? It's a rather strong laser. Stronger than this one. I could actually buy one that's this strong, but I don't like to carry it around with me. And they use the fact that a laser can be focused to a very small spot. We're going to be talking a lot about lasers in about 2 weeks. And you'll see that there are many features about the lasers that make them important. The thing for the laser is not the fact that it's the fact that it can be, not the fact that it's a single color, although that's related. The fact that you can focus it to a very fine spot. So what they do is they burn away a little bit of this, of that material. Then they put the flap back. And it heals very quickly. Of course, it's all on the inside that they've done this. And so you walk out of there, and you don't even have a Band-Aid on it. Okay? And now the shape of the cornea is a little bit different because some of the material has been removed. And if they did this just right, they give you basically perfect vision. I have lousy vision in my left eye, where I actually had major surgery 2 years ago. But on my right eye, I have basically perfect vision for infinity. That's LASIK surgery. Now look at this path. This light will come in like this. The light reflects off the retina. Some of it does. Some of it's absorbed. That's what you see. But a lot of it is reflected off. When it's reflected off, it comes back this way, right back to the person who was, to the camera. So if you have a camera, and here's your camera, and you're going to take a picture, and you have a little flash bulb right here. And here's an eye, whether it's you or a deer or whatever. The light from the flash bulb comes to the eye, bounces off the retina, comes back in the same direction. And it's usually spread out enough that some of it goes into the lens of the camera. So your eye is what's called a retroreflector. And that's why the light from your face, light from your face comes and spreads out in every which direction. But the light from your retina comes right back to the camera. It doesn't spread out. Because of this geometry here, which which I just covered up, the light coming in bounces, comes back in the same direction. It spreads out over here, but it's focused right back at the camera. So this is where the red eye comes from. The retina of the eye is a little bit red. For some animals, it's a little bit blue. Different animals have different things. Other animals, if you have a really big pupil, big opening here, then you get a lot of light coming back and you have very bad red eye. So what some of the camera companies do is they have a red eye reduction. The red eye reduction works as follows. They blind the poor person twice. So what they do is they flash at you without taking a picture. Ugh. When that happens, the pupil of your eye contracts, makes it small. So there's this covering here that closes down because of the bright eye, so less light gets in. And a half second later, your pupil is down and closed, and you're a little beady-eyed. And then they take the picture. Now here's my objection to that. When you're looking at something you like a girlfriend or boyfriend, you look at something you like, your pupil tends to open up. And because your pupil tends to open up when you look at something you like, the person who's looking at you knows you like them. And then if you got the right thing going here, I still remember looking at my wife-to-be, looking at her, and I saw her pupils were dilated as, I looked at that, and there's biology has designed it so that when someone finds you attractive, you find them attractive. Otherwise, we'd never do this silly thing called having children. So I can almost feel my eyes bursting as my pupils open up like this. So she found me even more attractive, and pretty soon we had 2 kids. Now, what the red eye reduction does is by flashing, so your pupil goes down, so there's less reflection coming back, it makes you into a less attractive person in the photograph. That's why I don't like red eye reduction. Now, there's an alternative to red eye reduction. It's called putting the flash up here. The only problem, that'll work. And actually, old cameras used to have extenders to put the flash up high. The light goes right back to the flash, but doesn't get in the camera lens, no red eye. Only trouble with this is it tends to give harsh shadows. If this is a point-like thing of light, and here's the head, the light is shining, let's say, on the chin, and there's a big shadow back here. This is all in shade, a shadow. This part here is all in shadow. But the camera lens, because it's lower, can see it. So you tend to have these shadows in the picture, which people don't like either. Now, the professional photographer has an easy solution. They take the light and they spread it out. They have a big flash instead of a pointy little flash. That way you don't get harsh shadows because light's coming from many different directions. And the light all comes back to this, but it comes back to this in a, some of it's coming here, some's coming here, some's coming here. It gets spread out, so you don't get that much into the camera lens. So the professional photographer will have a big flash, or sometimes what they'll do is they'll use a reflector. In fact, I take reflective photographs a lot. I have my camera with this little flash on it. I put a piece of paper in it, reflecting the flash up to the ceiling, which then comes down and spreads out. Other people will just put a piece of paper in front, so light hitting this spreads out. It takes more light to do that, but it gets rid of both red eye and the harsh shadows. Red eye is used by the military with radar. I was expecting to have a little setup here, but we forgot to get it, in which another way you can have a retroreflector is with a corner reflector. Light coming in, bounces, and comes back the same way. Turns out that even if the corner reflector is tilted a little bit, whoops, I'm not doing that well here. It has to be a right angle. Okay, even if it's tilted a little bit, the light comes in, grazing bounce, and then a steep bounce, and it comes back parallel. For those of you who like geometry, prove that. It turns out to be true. This will always come back parallel to that if you're bouncing off a corner. A neat little geometry thing for those of you who instead of going out on Saturday nights, like to play with math. Not to reinforce the image of the nerd. So try it. It's sort of fun to prove. And so corners can be used to reflect light And we had one. I'll try to bring it in next time. We're supposed to have it today. Another thing you can do is reflect any electromagnetic wave, like radar, from a corner. So, for example, if you're sending a radar down on a scene from an airplane, and there's an airport, at the airport they can put a corner reflector. And then your radar will be sending off these microwaves looking for reflections. You're getting reflections. Whoa, there's a big reflection right there. Well, what's really happening is you send the radar wave out, it bounces off the scenery, goes every which way. When it hits the corner reflector, it comes right back to you. If you're a bicycler, you use retroreflectors. You may not know it. If you are a driver, when you look at a stop sign, they're using retroreflectors. Let me talk about the retroreflector of the stop sign or of the bicycle. Here's the missing diagram. Okay, let's look at the stop sign. Here you have a stop sign, and it's nice and red. And the car is going to come by. And here's the car. And I'll just draw two important parts of the car. There's the headlamps, and then there's the driver. The stop sign is not just red. Maybe you've noticed when you're driving at night, the stop sign seems to light up. But only when you are driving at it. It doesn't light up from other cars. Interesting thing to notice. Why is that? What they have on the surface of the light bulb is they have these tiny little beads. I want to draw them as big, but they're tiny. But you look at a stop sign, you can feel them. And many of you have reflectors on your bicycles that do the same thing. So here's the little bead. The bead is made out of a plastic or glass such that light hitting the bead, it hits it just like it might hit your eye. Focused on the back, bounces back, the light comes back. It comes in and comes out on the same path. The light coming down here will go boom, boom, and come back along the same path. The beads are like your eye. They're like little red eyes, except you cover the beads over the whole surface. You make them red on the back where the red part of the stop sign is, white on the back where the white part of the stop sign is, so it will say stop in red and white. And the driver, who is close to his own headlights, well, enough of this light will come back and hit the driver that you'll see when you're driving this lit up stop sign. But no, it won't be lit up for anybody else because the light is coming back to you. If you're a bicycler, not bad. You may put a little reflector back here, a little thing. And it consists typically of little beads or maybe of a thing made up of little corners. Either one will work. If you do that, then if a car is driving that away from you, he won't see you and you don't care. But if he's driving right at you, I mean, drivers, they don't notice bicyclers. They don't notice motorcyclists either. They are looking for other cars or sometimes for people who are walking. But bicycles are odd enough that they don't notice them. You put a little thing like this on there, and when their headlights hit you, which means they're coming towards you, the bright spot comes right back at them, and they say, "What's that?" Well, this is what the retroreflectors you do on your bicycles. Some friends of mine back years ago built a retroreflector about this big to put on the moon. It was delivered there by the Apollo astronauts. They put this on the moon, and then a laser from the Earth was directed at the moon. But if it just hit the moon, the light would have spread out in every direction, and not enough light would have come back to the Earth. But with a retroreflector there, the light comes right back towards the Earth. And that way they were able to see the reflected light. And what they did is just by timing it to get a precise measure of the distance to the moon. Why do you care to know the distance to the moon to a centimeter or so? Well, it was actually a test of general relativity, which predicts that the orbit of the moon will be a little bit different if general relativity is correct than it would otherwise be. So by measuring the position of the moon to a few centimeters and watching it move through space, you could actually test general relativity. So it was an interesting thing to do. sometime in the 1960s, some engineers at Lockheed made careful studies of radar reflecting from airplanes. And you think of, you shine a flashlight on something, and it gets bright. And what's happening is the light hits me, spreads out in every direction, and then some of that light tends to get into your eye. Radar works a little bit differently. In a radar system, what you typically have is a radar transmitter. It's often a dish. The transmitter is right here. It sends the radar signal backwards onto the dish, spread out like this. And that sends the signal forward. If the shape of this dish is what's called a parabola, that's the shape that will take all this light and bend it just the right amount at each point so it all goes in the same direction. So this way, with the radar, what you do is you send a beam of radar up. You're not flooding everything with a big signal. You're sending a beam. Then what you have to do is scan that beam back and forth. It's quite different from the way our eye works. A little bit like a TV. A TV has a little picture here, then here, then here, then here, and it goes fast, and it creates a picture by changing the brightness, but it's scanning. Not like a photograph where the whole picture is there and you shine light on the whole thing. It's just one little spot at a time with a TV screen. With radar, what you do is you send this beam up. Now, typically, the old radar used to be just send a beam here, and then you move it around in a circle, and it's broad enough, looking on the horizon, that any airplane will do it. If you really want to be detailed, you make it a small beam, needs a big antenna, and you have to go up and down as well as sideways. But for the most part, you're looking at things that are far away, so all you do is scan the horizon like this. And then, the old movies, they show this screen. And they show this line. And the line is sweeping around. That represents the direction in which the radar beam on the map is pointing. And then it's sending out pulses, not a constant light, not like this, but more like pulse, 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 pulse. And then it looks to see of the pulses coming back. And from the time it takes them to come back, round trip time, it knows the distance. So that's how radar works. And if it gets a strong signal coming back at a certain time, it puts a blip on the screen, like that. Now this thing sweeps around, continues to sweep around. The old radar screens had these phosphorescent screens that when they got a big blip on them, the blip would last there for a second or two, just so the radar operator wouldn't forget it. So you see the old movies with the radar sweeping around, there's a blip. That's what's happening. It's the beam going out, looking at the time of the reflection. That puts a blip on the screen, and that tells the angle, that's where, the direction it is, and this gives you the distance. And that's how the old radar screens work. Now, of course, they feed them into a computer, and you get a much more elaborate display, but they didn't have that back then. So here is, that's the radar. Now, what it turned out came as a big surprise to everybody, super classified secret at that time, was that airplanes, they're messy things, right? They have, here's an airplane, there's the pilot, and there's the thing there, and there's the wing here, and the wing there, and the engine, and all this messy stuff. So what they did is they made studies of what is the radar reflecting from. And there are a couple things. A little of it comes from the front, of course. That's a small signal. But if it's a blunt front of the airplane, that could be, when they talk about the area that reflects, that's called the radar cross-section, cross-sectional area. Front of the plane might be a square meter. Inside the cockpit, it turns out there are usually lots of right angles. A right angle makes a retroreflector. So some of the signal will actually come back from in there from these retroreflectors. The wings, this is often a right angle, and there's a right angle between this wing and the plane itself. And so it turns out that a large fraction of the reflection comes from the front of the plane or from these right angles that are all over the plane. And so, what do we do about this? Let's make an airplane that has no front surface and no right angles. And then we'll call it a stealth airplane. And that was the key secret. Still is. It's not a secret anymore, but that was this key secret of stealth airplanes. So the first stealth airplanes, if you get a look at, I should bring in a picture, some of these original stealth fighters, they look like this. One is they have very pointy noses. They just don't want much area up there in front. They want a square millimeter, not a square meter. of cross-section because a square millimeter reflects much, much less. Secondly, they made these surfaces absolutely flat. The idea being that the radar would reflect off like this. Now, it turns out that the radar transmitter, the signal comes out, it comes right back to the radar transmitter, and it gets focused into this. And this now is, in that interval, changed from a transmitter to a receiver. Put a switch in there. So they send the signal out, and then they wait for it to come back. It's almost as if your eye were a flashlight. I mean, you know, so I think the writer of Superman thought that Superman that you see by sending out waves from your eye like a flashlight. So Superman had X-ray vision, but sometimes he used his X-ray vision to cut holes in things because his eyes were transmitters, like radar, unlike ours, which are just receivers. Now, if the signal doesn't bounce straight back, if it bounces off a mirror, radar doesn't see it. Now, some of it will come off this front tip. So they tried doing other things too, like putting special things that don't reflect radar very much. There's only so much you can do on that. The original stealth airplanes, if you look at them, they're weird. They consist of all these right angles. Not right angles, I'm saying. They don't have any right angles. Even if you look at them from the front, you find that instead of having one surface that goes up sitting on the surface here, hey, that makes a right angle. What they would do is they'd put two of them and tilt them. They don't want any right angles because it's the right angle that makes for the retroreflector. So they had planes made up of flat surfaces. Getting something like that to fly is not easy, but they could do it by using computers. It was very hard to fly, but at least you wouldn't be picked up on radar. And I think the first test of this was in the first Iraq War, where our stealth fighters were used for the first time. And stealth bombers, too. That is the key secret of stealth. These days, they're getting better at it. You can have a curved surface here, as long as you get nothing reflecting back. It's okay for it to be curved. So some of the more modern planes have curved surfaces. When they proved the principle, they had to really make it exaggerated. So that's the idea of radar, of stealth. I want to show you this demo, just because it took 2 days to set it up. And if we can have the lights down, maybe we'll see it better. This is nothing more than a laser beam going through some water that's been set up with sugar syrup for 2 days. What happens is the sugar tends to settle near the bottom if you really just leave it alone. And so the top of the water isn't as sweet as the bottom of the water. Now, sugar, it turns out, also slows down the light when you have sugar dissolved in the water. So here we've set up a situation where light going into the water, the bottom will be slowed down more than the top. And that means it'll tend to bend towards the bottom. And that's what you can see here. How well does that show up there on the screen? Can you show this thing over here? It's showing the screen, I think. What I want to see is this tank, this green tank here. Turn this thing off, maybe. Does this show up at all? You may be able to see it without the projector. But what we do is we have a laser beam coming in. Where's the laser beam coming from? There it is. It's right here. So the laser beam comes right in. The beam is going horizontally. Oh, look at that. That's an interesting angle. That's using this video camera right here. Okay, well, you see, but really, if a front view would be better if you have a capability of focusing in on that, because the beam comes horizontally and then it bends downward. Finally, it bounces off the bottom, and then it bounces back up and goes horizontally again. So it's forming like a little mini sound channel. You can't get the front video on that. It has to be just a side one. So let me draw a diagram of what it is you would see if you could see it. There's the beam coming in, and it bounces right there, and then goes, oh, there we go. So here's the beam coming in. Yeah, very good. That's perfect. So it's coming in horizontally, and see how it bends downward. That's because the light is slower at the bottom. And then it reflects off the bottom and comes back up. But if we had 30 feet of this, what you see is going bounce, 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 bounce. Curves very gradually. Okay, thank you very much for that. So let's have the lights back on. For a mirage, remember, it works just the opposite way. For a mirage, the light, instead of bending downward, because the air down here is hotter, tends to bend upward. And so when you look down at this, you see blue light coming from the ground, the blue light from the sky. You're looking at the sky by looking down. Psychologically, you see blue down there, that must be water. That's what a mirage is. You can get best mirages are on highways on hot days because the black asphalt of the highway really gets hot. It gets the sun hitting it, the black heats it up, and it gets hot. So you get this hot air over the highway, more so than you would over grass. Other good place, which I recommend, is the Sahara Desert, where I was last January and got some very nice mirages there. The other thing that happens is maybe you're seeing the blue sky, but there may also be a mountain or something here, and you get a reflection of the mountain just like a mirror. Now, oh boy, so many things we have to cover. What have we covered? We've covered stealth. We've covered retroreflectors. Let's talk about colors. Light from the sun has many different frequencies. We'll be talking more about this next week. Many different frequencies. The low frequencies are red. Lower than that is the infrared, which our eyes don't see. Most of the light from the sun comes between the red and the blue. And that's why our eyes evolved for red and blue. If it didn't come from that, we would have eyes that would be sensitive to other colors. But most of the light comes from there, and we get the spectrum of colors is just the sensitivity of the. Okay, so if we say here positive versus frequency, going this way, 6 times 10 to the 14th number you don't have to know is blue is basically green, and up here is blue, and over here is red, and your eye's not equally sensitive to that. And if you get down to the infrared, IR, or the UV, ultraviolet, your eye doesn't see them. But you'll come across these terms all the time. You need to know this. You need to know that infrared is a lower frequency of light. Sometimes it's called heat radiation. This is really what next week is about. Ultraviolet is a higher frequency. It can cause skin cancer. It becomes really important for the future of the ozone layer, for example. Infrared is really important for global warming. Understanding the infrared is the key to understanding the global warming problem. Understanding UV is the key to understanding the atmospheric ozone problem. So these things will be very important. But these are not the things that we see. We see between red and blue. How do we see between red and blue? We don't, it's interesting. How do you make a detector in the eye that can see a tiny little spot of light and tell whether it's red or blue? The way nature figured this out is it doesn't put in just one sensor. It puts in 3 sensors. Your eye, the retina of your eye, actually has 4 sensors altogether. So the back of your, and they're all these little sensitive cells. The green ones will give a stronger signal when the light is green. The red ones will give a stronger signal when the light is red. The blue ones give a stronger signal when the light is blue. What if it's in between? Well, the red sensors actually sense a whole range of colors, and the green sensors also do a whole range of colors. The red and the green aren't really that far apart as I drew them here. Then they're the blue sensors. So what your brain does, and then it has some sensors that just see brightness, period, without any sensitivity for color. Those are the most sensitive of all, the ones that don't see color. Little thing for the movies here. Okay, go out when it's dark and look around and look at the colors you see, and you'll see faded colors in the darkness. You won't see very bright colors. The reason is you're only using the sensors that respond to basically black and white. The color sensors, because they only pick up a narrow range of light, aren't as sensitive. So when the light is dim, almost everything you see are with your non-color sensors. And try this at night. And then turn on the light. Oh, we can do this in the room. Can we turn down the lights of the room? And will the colors become, look around, let's see if the colors, just turn them down again, and see if the colors become less vivid. Okay, could we turn down the lights of the room? I guess, or yes, go back in there. Turn them down everywhere in the room, and you will still see colors, but keep on going. There, okay, now look around, and your eyes will adjust. What's happening is the pupil of your eye is expanding because it's dark to let in more light. But look around, and you still see people, but you don't see that much in the way of color. Now, I didn't wear a very colorful shirt today. I should have. The laser is still a brilliant green because that's bright. Okay, so let me... But most of the other colors are somewhat muted. Let's turn the lights back on now, and the colors will return as you look around at everybody. Now the colors become a dramatic part of everything. This is useful if you're a movie maker. Because if you're a movie maker, you have a real problem if you're making a movie at night, because you don't have much light. So what do? Digital movies, it's easy, but even with film movies, it's not that hard to do. What you do is you film during the day. But then when you process the film, you reduce the colors. And as the color goes away, the person who's watching the movie will see the movie, and they will have the automatic perception that it is at night because they don't see much in the way of colors. They say muted colors. So movie makers do this all the time. They don't want to film at night. Sometimes you'll see rather sharp shadows at night. You say, oh, it must be a bright moon. Nah, it's a bright sun. And all they have done is turn down the colors so that you, who are accustomed to seeing not much in the way of colors, will think this is a nighttime scene. Now, the red and the green actually are closer than I drew here. They really overlap just a little bit like this, and then the blue is over here. So why do red and green look so different? Well, that's our brain. Our brain is saying, oh, it's different. How does the brain know it's different? Suppose there's a color that's exactly this frequency versus this frequency. This one will look green to us, and this one will look red to us, even though they're so similar. But this is the brain doing the processing. You see, if the signal is here, you're getting a strong red response. The red sensor is picking up the signal. And the green sensor is only picking up half a signal, or 3/4 of a signal. So when the red signal is stronger than the green signal, the brain says, that's red, and it lets you know it by displaying red to you. On the other hand, the green sensor is, if a light is a little bit different in frequency, closer to the green, then what happens is this one responds. And you get more green than red, and your brain says, more green than red, let me send a signal to the human soul saying, this is really green. So it's this processing going on. Let me draw yet a more accurate image of this thing. The red looks like this. The green looks more like this. The fact is, red light, you have a lot of intense red light, and your eye doesn't respond very much, but to green light, it responds a lot. So most of us switched over to green lasers, not because they have any more energy, not because they will burn my hand any more than an ordinary red laser, but the eye sees the green a lot more. Some people are colorblind. About 10% of the men in this room are colorblind. Colorblind means you don't have red, green, and blue. Hey, why waste all that effort with red and green? What's it good for? Well, stoplights? Hey, we didn't evolve to be good at stoplights. So what do you need it for? Why not just fill the whole thing up with green sensors? Hey, then you'll have more sensitivity. You'll be able to see things in the dark better. You'll be able to see that tiger in the woods or the lion in the jungle because you will see better at night if you give up some of your color vision by putting in more green sensors than red sensors. So a certain subset of us evolved to be what we call colorblind. You can't tell the difference between red and green. One of these things is missing. So you get a signal there. It's a good bright signal. But you have twice as many of them, so you see more of the light. But you can't quite distinguish the traffic light except by seeing if it's at the top or the bottom. And that's how people who are colorblind do that. Now, in some sense, we are all colorblind. And the reason is we only have 3 sensors. And with 3 sensors, you could have colors that, well, for example, suppose I have these 3 sensors here, and I put in a little bit of red, a little bit of green, and a little bit of blue, so that all three sensors get lit up. They all get signal coming in. In that case, I will see the same thing as if I look at white light. White light is light that has all frequencies present. Basically means all three of my sensors are responding. And if I do that, my eye can't tell the difference between white light and three colors mixed together. It can't tell the difference. There is a difference. I just can't tell. It's just like the colorblind person cannot tell the difference between red and green. Well, you can't tell the difference between red, red, green, and blue and white because your eye only senses three frequencies. Leads to this great optical illusion. And the whole color display industry, it's even used for printing color pictures. It was the great breakthrough to realize you don't have to put every color down there. Just put in three colors, one for each of the sensors of the eye. On a computer screen, all you need is red, green, and blue. Because all you want to do is excite the red sensor, the green sensor, the blue sensor. If you excite them all, the eye, the brain will say, oh, that must be white light. It's not white light. It's red, green, and blue light. It doesn't contain all those other frequencies in it. The sun has all those frequencies in it. But on a computer screen, it doesn't. So you get this wonderful optical illusion. You look up really close, and you see the red, green, and blue dots. But as you go back, so you don't resolve them anymore, it turns into white. It's a wonderful optical illusion. You're fooling the eye. You do it with printed paper, too. You look at the printed paper. They use three other colors for prints. That's because the prints, the inks tend to overlap. When they overlap, when red and green overlap on a printed page, you don't get both red and green. In fact, what happens is they cut each other out. So they use other colors. They use magenta and cyan on the printed page. But it's the same principle. What they're trying to do is excite the three sensors. All you need are really three colors. And you can stimulate the eye into thinking it's any color you want. They mix in other colors just for various technical reasons. Sometimes you'll have five-color prints. Sometimes they'll put black and white in there because the paper is ordinarily white and you want it to be black. You have to put in a lot of three different inks to absorb all the colors. They'll put black in. But the basic idea is you fool the eye by putting those three colors. That doesn't mean there's not more information there. I mean, if suppose you are spying on something and you see a white light and you'd like to know, wait, is that a sunlight on a piece of paper or is that a computer screen? Your eye can't tell the difference from the color. But throw in four sensors. Some people are reputed to have four different color sensors, by the way, super color. At that point, they'll see there's a difference. Well, why stop at four? How about 20 colors? Not only is that done, but it's one of the hot technologies of the current era. It's called multispectral. It's basically saying, hey, the eye is limited, but I can make a machine that picks up 20 colors. I can make a machine that picks up 1,000 colors. Turns out the more colors you pick up, the more you can tell. By picking up many colors, you can look at a smokestack, and you can tell what gases are in that smokestack. You can look at your grape crop. Tim Mondavi, a friend of mine, was a chief winemaker for Mondavi Wines. He would hire people to fly over his vineyards and take multispectral. Now remember what multispectral is. It means in addition to, you have all these colors coming up which the eye only notices 3. If you make a camera that detects 30, you see a lot of things that would look the same to the eye. You could see, for example, if your crop has some blight on it, if it's not getting enough water. The colors may be the same to the human eye, but there are really more colors there. We are all colorblind. On the other hand, if you start breaking it up like that, you have to take a longer exposure because each sensor is getting less color. The backs of your cameras, when you have a digital camera, what they have are 3 different color sensors in the back. Every pixel is really 3 pixels. Actually, it's a little bit of a lie. If you have 1 million pixels, you have 1 million sensors, but typically half of them are green, 1/4 of them are red, and 1/4 of them are blue. That's the way it works in the back of a digital camera. And they're all close together. And the digital camera takes these signals and measures the amount of red, green, and blue, puts that on the computer, on the chip. When you print that out, the printer then reproduces the amount of red, green, and blue, and you look at it, and there's the illusion. But if you look at it up close with a magnifying glass, you'll see those colors aren't there. There are only 3 colors. You're fooling the eye into thinking there are all these colors. And once again, multispectral can tell lots of things. A lot of remote sensing. You can look at a rock and from the color tell what rock it is. Now, the best geologists I know cannot do that by standing 10 feet away. They have to get up close and look at the crystal structure and so on. The information is there in the color. It's just that the human eye doesn't sense it because we only have 3 colors, or 2 if you're colorblind. Actually, that's not including the black and white sensors. So only 3 color sensors you have. But with multispectral, you can identify the kind of rock. All sorts of things you can do with multispectral. So keep your eyes open for the word multispectral. You'll see it in a lot of places. When you take the light from the sun, this flashlight isn't very multispectral. I like this flashlight because it's one of the super new flashlights, new high-tech flashlights. And has a tiny little battery in it, and it's pretty bright. The flashlight has a quantum mechanical light-emitting diode inside of it instead of the typical filament. And it has a very small spot of light. That's what makes it so good. So here's this tiny little spot of light. Some of the light, of course, comes out this way. What they do is they have this big parabolic reflector, so any of the light that comes out over this region gets reflected straight back. So you get 2 things. You get the bright spot in the middle, and then you get the larger spot of the light that's coming right off that spot. Send this through a piece of glass, and it slows down. How much does it slow down? Glass typically by a factor of 1.5. Okay, so if you want to know how fast it's going, it's not going a foot every computer cycle. It's going a foot divided by 1.5. So that's about 8 inches. Those are 8 inches when going through glass. Depends on the color. Some colors go a little bit slower. Some go a little bit faster. I wrote that down here in this chart. For glass, this is the factor which you slow down for red, yellow, and blue light. That's the slowdown factor. It's called the index of refraction. It's how much the light slows down. Now, suppose light goes in at an angle. It will bend because of the fact that one side is going slower. Different colors will bend different amounts. Now, that's given the word, it's called dispersion. I don't see any reason for you to learn that word, dispersion. But it means that the light going through a wedge like that will bend different amounts, and you'll get different colors. That's what gives rise to rainbows. In a rainbow, light bouncing through a glass droplet. Here's not a glass droplet, a water droplet in the sky. The sun may be over here. And you're over here. And the light is hitting the sun. And some of it gets inside, bounces off the back, but it's not a retroreflector. Because it doesn't focus it that well. So it doesn't come back in the same direction. It's water, it's not glass. It doesn't come back. It doesn't have the right slowdown factor. So in a raindrop, it comes out at an angle like that. And here's the light that comes out, and this one might be the blue light that comes this way. And the red light will actually come out this way. So that's what happens in a red rainbow. The blue and the red separate like that because they have slightly different velocities, slightly different index of refraction. So look, you're looking at the rainbow, you don't see any red light, you just see blue. But wait a minute, rainbows are red, green, and blue. So what happens to the red light? Well, it goes and hits your chin. So you don't see it. But wait, there's another droplet up here. And for this droplet, you get that bouncing. And here comes the blue light, which you don't see because it comes over your head. And then here comes the red light, which bounces like this, and it comes right to your eye. So you see it's a different droplet for the red and a different droplet for the blue. It's wherever the droplet, if the droplet's at just the right place, so the red light gets to you, then you see red. If it's at just the right place where the blue light gets to you, you see blue. So when you look up, what you're looking at, you see there's zillions of raindrops here. Many, many raindrops. You don't see them because they're too tiny. And if you look straight ahead, let's say this is looking straight ahead, there's going to be a range here of raindrops that are just the right angle to give back blue light. They're just the right angle that's where the light coming in through this spherical raindrop will bend through just the right angle to get to your eye. And because it's spherical, it doesn't matter whether it's here, here, or here, it'll just get through and you'll see the blue light there. And there'll be another set of raindrops that give you the red light. They're different raindrops. And up here, the raindrops will give you nothing. Because they're bending the light, but it doesn't get to your eye. And here's a little interesting thing you should observe next time you look at a rainbow. There is a region down here where, in fact, every droplet will give you red and blue and green in this region. I want you to notice that next time you look at a rainbow. By the way to find a rainbow is if the sun comes out. Oh, the sun's out. But wait a minute. It's raining. That's because the cloud's up there and the sun's over there. Ah. Well, let me look in the opposite direction too. There's the rainbow. Anytime the sun is shining on the rain, and it's shining from behind your head, maybe it's raining over there, and the sun is out. But if the sun is shining on the rain, the bounce back will give you the rainbow. You can get very good at spotting rainbows this way. Every time it's raining out, just know you look in the opposite direction of the sun. If the sunlight's shining on the rain, you'll get this. Now, what am I doing here? Okay, so in this region, you'll get red, green, and blue. In this region, the blue. In this region, the red. What will you notice in this region? You'll notice it will be bright. That's what I want you to notice. You look at a rainbow, and the rainbow is the edge, the red and blue edge of a whole bright region. I want you to notice that next time you see a rainbow. You'll even see it in photos of rainbows. Only the greatest artists actually do that. Artists are supposed to be people who can see things better than we can. But sometimes physics helps you notice things. A lot of photos of rainbows don't show this region. Now, there's sometimes a double rainbow. It's another rainbow up here. That comes about because there's another way the light can get to you from the sun, and that is to bounce around inside the rainbow twice and come to you. And then you see the other double rainbow. I don't want to spend too much time on rainbows because it's not really important for future presidents. I do want to show you this thing. So let me try turning this on. I hope I can make it work. A little bright light here. Oh, by the way, before I'll leave this on now, but before I leave this topic, noisy there, aren't you? You'll notice diamond has a much bigger index of refraction, so it bends light even more. And more importantly, the colors differ from each other by so much that the colors coming from a diamond are even brighter. I mean, you get more, the separation of the colors is greater. That makes diamonds sparkle. What you're seeing are the different colors. So I don't know if we can see this here, but the kind of sparkling you get from a diamond comes about because the light going in comes out at with different colors. The color which happens to be pointed at your eye is the one that you see. And as this thing moves, it's a different color pointing at your eye. You get the sparkling. Now, this is not actually a diamond. This is what's called a cubic zirconia. If you look at the cubic zirconia, you'll see the differences between the indices are bigger than that of a diamond. What that means is that by every standard, every reasonable standard, a cubic zirconia is prettier than a diamond. Well, that got De Beers kind of worried. Because why would anybody ever want a diamond when you wear a cubic zirconia and have something that's even prettier than a diamond? So De Beers has this wonderful advertising ploy. This is just wonderful. They can say, well, that's no good. It's not expensive. It's too cheap. How can you prove to someone you love them by giving them a cubic zirconia? I'm not kidding. This is really what they do. You'll see this in the ads. Okay? And then they'll look at this and say, oh, that's obviously fake. Too much color. Too much fire. It's not authentic. No, it's just prettier. Okay, but it's not a diamond, so we're not giving them an expensive diamond. Expense is totally artificial in the diamond business. It is a monopoly. Now, it's not quite a monopoly, it's a cartel, but the way it works is that if someone, let's suppose you in your backyard discover diamonds, and you say, hey, I'm going to sell them, and I'll sell them cheaper than De Beers. Okay? So I'll make lots of money. Now, you found them in your own backyard. De Beers has this huge market, this huge amount of diamonds everywhere. And they'll say, oh, he's selling those and he's selling them cheaper than us. Now, his kind of diamonds have this little bit of blue tinge and all this extra color and so on. Yeah, they're really very pretty, aren't they? Well, among our different kinds of diamonds, let's find the ones that are similar to his. Okay, here they are. They're similar to Muller's diamonds. Okay, let's dump these on the market cheap and say these are crappy diamonds. I'm not kidding. This is what they do. And so I am put out of business because I only have crappy diamonds. Unless I agree ahead of time with De Beers to charge, a lot of money for this, or at least I know what they'll do to me, so I charge a lot of money. And then they're happy, because I don't have very many diamonds compared to theirs, but they're not going to let me undercut them. They're going to put me out of business. You think this would be illegal? Well, we don't have a world government. So it's, what can you do? De Beers is located elsewhere. So here's what I ask. I don't ask this, I just suggest it. If any of you wind up marrying each other or anybody else, and based on your knowledge of physics, you decide that you'll use the prettier stone. This stone here costs, I think, about $50. Prettier than diamond. Instead of the expensive stone diamond, which is expensive because De Beers controls it and makes it expensive, send me an email and let me know. It warms my heart when I save you thousands of dollars. Now, what I want to show you more about the color in different kinds of lights, and there are a couple of things I'm going to do here. Let's see if I can. We know light is a wave because of the fact that when it goes through a small hole, it spreads, and because we can get interference. Let me illustrate that interference. You take a thin film, like a soap bubble, and you've seen this on soap bubbles. You take a thin film and reflect light off it. Some of the light will reflect off the back of the film. Some of it will reflect off the front of the film. If the frequency is just right, so that this one's going a longer distance, but if it goes just the right longer distance so it's back in phase with this reflected light, then those colors will add and they will be brighter. For one color, they'll be exactly in phase. For another color, it's a different frequency. It's going the same extra distance, but because it's a different frequency, it'll be exactly out of phase, and they'll cancel. And so what you get over here may be cancel red, reinforce green. That might happen at this angle. At a different angle, over here, you notice because it's tilted, this light has to go much further than this light. And so over here, you may reinforce red and no green, depending on exactly the angle. Also, if the film has a different thickness. If the thickness changes, right now it may be giving you a nice green reflection, but if it gets thicker, it may give you the red reflection. Just because then the light has to go further, and now the green might cancel. So we have this demo that's set up to do that. I hope I can make it work. So this is a bright light. What I'm going to do is take a piece of soap film. So I'm just going to make a soap bubble and put it on the surface here. Could I have the lights down, please? Turn the lights down in the room. I do this just right. I turn off some of the other lights. We may be able to see the soap film over here. So really, lights down now. Dark, dark, dark. Hello? Yeah. Okay. Pooh. Actually, I was just shouting. That's not using the mic at all. Okay. Now, if you look on that soap film, you'll see the colors moving around. They kind of swim around. What you're seeing are the different thicknesses of the soap film. You're actually seeing it, I think, upside down, so the thickest part is near the bottom. That's where you're getting some cancellations. What happens if I blow on the soap film a little bit? Soap film just popped. Let me put another one there. You have seen this when you blew bubbles. You see the colors on it. And that's where the colors come from. Is there a film on that? Yeah. The film is so thin, it's hard to see. So those colors from a soap film come about because of this kind of interference. The regions where the green is reinforced, you see the stripes of it, the film I can tell is wedge-shaped because it gets gradually thicker, thick enough so that the green reinforces, then the yellow, then the red, and then it gets so thick that once again it's the green that's reinforcing as you go over that soap film. What did I do with my green laser? So I can point to this thing. But you can see what I'm talking about. So I like this demo. You can kind of fall asleep to it. It could be a good screensaver. I could just spend the last 15 minutes of the lecture with this thing on, and all you do is watch that and have sweet dreams. And then now, there's another place where this comes up, which is if you have anytime you have a thin film, you'll get this. A thin film on a camera lens can be used. These are called coated optics. When you go to a camera store, they'll ask you, do you want coated optics? The idea of coated optics is to make the reflection of as many colors as possible cancel on the reflection. If you make it thin enough, you can have almost, this is pretty thick. If you make it really thin, you have almost all the colors cancel on reflection. And that way, the light coming into the lens goes into the lens instead of reflecting off. That's what coated optics is. So let's have the lights back on this now. Turn this light off. It's another way you can get color. And, well, there are many ways. You could go through glass and it bends. You get the interference. This is a demonstration. Galileo should have recognized this. Where have you seen this before? Where have you seen these colors? To me, it looks really beautiful because I love these kind of colors. To other people, they say, oh, it looks like an oil slick. I love oil slicks. You look at an oil slick and you see those colors and you say, oh, light's a wave. How do we know it's a wave? Because you're getting interference. You're getting the light canceling. The red light is sometimes canceling, sometimes the blue light is canceling, sometimes the green. You get all these colors there. Newton should have realized when he looked at an oil slick that this was evidence that light is a wave, but he didn't. Now, one last thing here. Let me show you this. Okay, I think we're going to need some lights down again. I mentioned that light, when we have the slinky, light can be moving up and down, could be sideways, can be in between, but in between can be thought of as up and down and sideways at the same time. You're going, the field is basically going that way. We call those the different polarizations of light. If light is going up and down, as it is there, can we have all the lights off, please? So there's the light, but I have put a film in here that it's called a Polaroid film. What it does is it takes the sideways light and cuts it out completely. So only the up and down light comes. This is useful for Polaroid sunglasses. When light bounces off the surface of water or of a table or a road, it turns out it's the horizontally polarized light that bounces, and the other light is absorbed. So when you're looking at the surface of water, you don't realize this, but that reflected light is polarized. If you then put a vertical filter in front of your eye, that reflected light will be cut out. That's called stopping the glare. Glare doesn't just mean bright lights. The only thing this stuff stops is reflected light that has become polarized because it's reflected. This light is polarized. You can't really tell very easily. Some people can. They have a slight sensitivity to polarized light. They can tell it's polarized. You probably can't tell. Here's another Polaroid. Lets through the same polarized light. They both let through vertical light. If I rotate this, it lets through light going only this way. That's fine, because that's the way the light is going. But if I rotate it this way, then it won't let through that light, and it gets dark. This is how the display on your computer works. It doesn't actually physically rotate. What it does is it rotates electronically. It uses what's called a liquid crystal. Liquid crystal are atoms that line up, and where you can rotate them electronically. Every little square of your computer display, and of the future TVs, although these things are only beginning to hit the market, the liquid crystal, you have a fluorescent light bulb behind your laptop. It's the way they work. Any of these really flat screens, they have a fluorescent tube behind it. Then in front of it, you have these liquid crystals, which are polarizers that can be switched electronically. Some of them are red. They put little red, green, and blue filters in front of them. But the way they turn them on and off is by electronically switching the polarization. Liquid crystal displays use this polarization. Polarization is interesting because when light travels through a plastic or through other glass, sometimes that polarization will be rotated, and the amount that it's rotated depends on the color. Did you follow that? Light coming from here, if it goes through a piece of plastic, let's see what we have here. We have some plastic. Yeah, here's a piece of plastic. Okay. Light going through that, the polarization in different parts is rotating, and different colors are rotating different amounts. Can you see that? It's kind of hard to see, except for those rare few of you who have sensitivity to polarization. But let me put a piece of Polaroid here that lets through now only horizontally polarized light, and put it on top of this, and you see what you get here. Again, if we can have all the lights off, please. All those lights in the back. We want as much contrast as possible for this demo. You'll see the colors. Let me take a bigger sheet, just because it'll be a little bit more dramatic. There we go. That's better. How about, can you get those lights off? So now you're seeing it much prettier. Let me turn this thing off too. So what's happening here is normally light would not come through both of these Polaroids. But when it comes through one Polaroid, it's all polarized. It gets through the plastic that rotates it. Different colors rotate different amounts, so we're getting the color coming through. This can actually be very useful. And it's, here's an example. Suppose you're building a bridge. And here's, let me take this away. There's the bridge. Let me do it this way. There's a piece of the bridge. You make it out of plastic. And the bridge is going to be stressed. I'm squeezing it here to stress it. You notice what happens here? A little bit of it is getting dark. What's happening is that stressed region is rotating the polarization. So you can measure the stress in this by looking at the polarization. In fact, if I if I rotate it this way, it may be even better. Okay, so there it is. And now I squeeze on it. And you can see the stress in it. And so this is a good way to make a model of the bridge, stress it the way the bridge is going to be, and then you can see the stresses inside of it like this. A Scotch tape is stressed. Let's see. Here's a piece of cellophane. Let's see if this works. Is this stuff stressed? Let me put some Scotch tape on it. Here's a piece of Scotch tape. This is not the magic tape. This is the old-fashioned cellophane tape. I put it down there. Doesn't really show up very well. I have a whole bunch here of tape I put down on a sheet. Big pieces of tape on the sheet. As I lay them on top of each other, the thicknesses change. And you can see I'm not quite at the level of Mondrian or Jackson Pollock. I did it with equal speed to Jackson Pollock. I did this last time. Just sort of laying down the pieces. I forgot to bring tape with me today to lay it down. But as I rotate it, the different colors come through. This is using just polarized light. Now, one of the most common ways to, okay, lights back on, please. One of the more interesting ways to use Polaroid light is the following. Suppose I take the TV screen or a movie screen, and I project a picture on it, and I make the picture polarized. Now, I won't notice it. But if I put on a pair of Polaroid sunglasses, I'll only see the picture in one eye. This one, if this is horizontal and the picture is vertical, I'll only see that picture here. This one will be blank, be black. Now, on top of that picture, I put a separate picture, one that's horizontally polarized. And I make this one vertical, this one horizontal. Now, this eye will see only the vertical one. This one will see only the horizontal one. I'll see two different pictures with the two eyes. That's how Polaroid, that's how these 3D movies work. Because what they do is they project one image of the way something would look if you were over here. And they project the other image of the way it would look if you were over here. They want it to be right. They wouldn't go way over here and way over here. They'd show the way it looked if you were here and here, the distance of your two eyes. See, open one eye, hold a finger about 3 inches in front of your nose, and then open first your left eye and then your right eye. And you notice how the finger jumps back and forth when you switch that? Your eyes are getting different images. You open them both at the same time, and it's very confusing, but your brain knows what's going on. The finger's closer. It says it's closer, and you interpret that as saying it looks closer. That's what's happening. You get different images, your brain brings them together. You fool the eye by giving two different images, one from here and one from here. Except that's not much of an effect. If you do that, nobody would go to the 3D movies. If you look at me, you don't see me in much three-dimension. I mean, is this finger in front of my nose or behind it? You're not very good. You can tell that. So what they do in the 3D movies is they exaggerate the effect. By instead of having images here and here, the separation of the eyes, they go here and there. And over there. Then you could be 30 feet away from me, and you'd see that this is in front of my nose. Big effect. The effect leads to some weird things, which is why I think 3D movies have never really caught on. They're a nice gimmick. Because if I remember Buana Junction when I was a kid. And here it is, you're in the jungle, and the native comes, and he goes, woo, and he throws a spear right at you. Really great stuff. They still have these things at Disneyland. They have a few IMAX things where they do this. But it tends to be a gimmick and exaggerated because they exaggerate it. If they make it natural, it's not that much of an effect, because it turns out the difference, when you look at me from the back and open and close one eye and the other, you don't see much of a difference. Because the angle difference is so small. It's only if you're up really close, and so it makes a difference up close. Now, what have I missed? Diamonds, De Beers, multispectral polarizer, 3D diffract. Oh, blurring! Didn't do blurring. Okay, I got 1 minute to do blurring. And we'll have to come back to this next time. Light going through a hole tends to blur out a little bit. The formula is given right there. B equals L over dr. L is the wavelength of light, typically half a micron. That's in meters. D is the diameter of your lens. For your eye, it's just a few millimeters. For a big space telescope, it's 2.4 meters. R is the distance away. In this case, 200 kilometers. Put that together, and you get a blurring of 0.04 meters. That means the light will blur as much that it will blur out anything that is that size, about 4 centimeters. It means the space telescope, this $10 billion thing we put into space, this huge, monstrous telescope, if it were in low Earth orbit, which it isn't, and we're looking down at the ground, you'd be able to see things, it would blur things at about 4 centimeters. You could just barely maybe read blurry license plates at that distance if you took the huge space telescope and put it in low Earth orbit. Needless to say, a reasonable conclusion from this is that spy satellites cannot read license plates. If you go up into geosynchronous orbit, the same answer becomes 7 meters, which is 23 feet. We'll talk a little bit more about this next Tuesday.